How we do? Oh, so Amir is asking how to do this. Join the voice. So join the voice channel, and that's it. So for those people who are watching on live on YouTube, like, can you let us know whether you can hear everyone's voice? That'll be cool. I'm not live. Are you sure? Because it's seems to be okay. Cool. Okay, so there's a bit of a delay then. Your audio as well. You can hear yourself. Yeah, but I mean, I like your voice to be going through as well. So
No, Discord audio is not going through.
so
No, the Discord audio is not going through because that visualization for Discord is not.
yeah, I see how this works. I thought yeah. Can I? I'm not audible in this. Okay. Okay. What about now?
No, you're not. No, you're audible. You're audible now. Yeah.
Okay, perfect. I mean, I don't know. It's really a bit of a test. So I apologize to everyone who's listening live if the audio from the Discord doesn't come through. I really will try to fix these. Can anyone else, like on the Discord voice channel, say something?
Hello, hello.
Okay, perfect. I mean, I don't know.
Now it's moving actually. Yeah, now it's moving. I think it should be working now.
Cool. We'll just give it a couple more minutes and we'll start with discussion.
Yeah.
Because
So,
I can't hear anyone else. I see that Amir is in there. CJ Volts is in the channel as well.
I'm here. I'm just muted.
Ah, you're just muted. Hello, Amir.
Hey,
hey, Amir.
there.
So we'll just give it a couple more minutes, okay, and then we'll get started with the discussion.
Okay.
Yeah. Let's see.
So I'm muting myself right now. Please just tell me when you have to start.
Yeah, sure. Don't worry. I'm pretty much new on this. I'm really learning as we go. I mean, we can start if you guys want. It's I don't wanna, we don't have to stay here live forever. I just wanted to kind of understand. I wanted to kind of get a feeling of how whether you enjoyed the paper and sort of what were the takeaways from your side. I mean, we could just if we could just do a quick round if you guys want. Each of us, like, what was the most interesting thing that you found in the paper and kind of get the discussion started.
Okay. So I'll start. So what I liked about the paper was that it touched every aspect of quantum computing, you can say basically. So it was not restricted to any particular field. So if you're a newcomer to this community or newcomer to this field, then the paper gives you a good idea about what things you can expect from quantum computing and what are the basic principles on which quantum computing works. So it is a good, you can say, preliminary paper or the good beginner's paper. So yeah, that I can say was the highlight for me. Um, it had simple language and you can say relatable stuff.
Yeah, cool. I mean, um, I don't know. Do you guys want to go ahead, or I mean, I can. I do have. So from my perspective, I totally agree. I kind of enjoyed the lightweight style that it had. I kind of feel like it was maybe a bit both good for people like with with in-depth knowledge, but as well as kind of business people that are looking into what's kind of the business potential and all these. And I think that the paper does a really good job in not kind of filling up the hype in the field, right? So I think that's also important. And there's nevertheless one thing one thing that in general kind of bothered me more is the fact that it seems like to follow the same pattern like most of the discussions online nowadays, which is on what types of problems you can solve or quantum computing can solve.
Yeah,
But there's no like focus on, for example, what systems can you build, right? And by systems I mean like with physical computing, you can also, of course, run algorithms that do stuff like the GPU does, or even without a GPU, but like particular, really specific types of algorithms. But you can also build systems, right? Like you can actually build systems that work, that have user input and stuff like that. And I feel there's not much work done explore in this direction. But this is probably something that needs to be more, kind of maybe the industry to be in or the field to be in a more mature moment. I don't know.
yeah, yeah.
What about you guys? Or Amir, like, did you like the paper? Did you have to go through all of it?
Yeah, I enjoyed the paper primarily because of I didn't actually have time to reread it. I had read it not too long ago. I think maybe like 1 or 2 months ago. But I like primarily the section when he goes through some of the early areas that can benefit from quantum computing, like deep learning, matrix inversion, the recommendation systems. He goes through and just lays out, where we're at, like what we can actually like, special nature of maybe how we have to structure the problems, those sorts of things. So I really appreciated that kind of analysis because it was, when I read this at the time, it was the first time I had seen anyone do that.
Okay.
And it's helpful as a newcomer to see like some criticism about like, constructive criticism about actually how valuable these things are and like what are the constraints.
Exactly.
And from all the, what was the date of the paper actually? Was it 2018 or 17, or what was the date?
It's 2018.
2018.
2018, yeah.
And is this the paper where he coins the NISQ term actually? Do you know that, or?
No, that's from 2012.
Yeah,
So
that's a different paper.
Fresco wrote a paper where he introduced that term the first time.
Okay.
I forget what it's called though. It's like
It's also the name quantum computing on a NISQ era. I don't remember the name.
yeah, C skill. Yeah.
And another important thing that I like about this paper was the way he describes entanglement. He doesn't describe it to be anything magical, or he keeps things simple. The example which he used, the example of the book, that was a very, you can say, intuitive example.
Oh yeah, I agree. That was a really interesting example, that the information is encoded in not just the pages, but like, I mean, actually, it's not that it's not just in the pages. He literally says it's not in the pages, but it's in the sequence in which the pages are sort of arranged, right?
Exactly. Yeah.
Yeah,
Yeah.
that's.
Yeah.
But like from.
So I was going to say, I think you are correct. It is actually this paper that introduced the term NISQ. I thought it was earlier. His previous paper was quantum computing in the entanglement frontier, and that was in 2012, but that doesn't actually mention the words NISQ.
That's probably where he introduces the quantum supremacy term, right?
Yeah, that was where I think.
Okay, because here he seems to really introduce the concept, but like I don't know, it's from all this stuff. Like, do you think that he, or do you kind of feel like there's any of the angles that are missing? Like, because it's really, I mean, I don't know. What do you think about what I said? Like in terms of the quantum or the building systems. I don't know if I explained myself.
Yeah, so basically, it's also you can say a 2-year-old paper is also considered to be an old paper. So things have gone uphill from 2018, of course. New applications about quantum computing have come into play, and but I don't actually agree because I think he was able to actually touch every aspect. Um, I'm just saying touch every aspect, not a complete description, of course. But yeah,
What do you mean? I didn't get your last point.
yeah. So exactly, wasn't able to hear you properly. What was your point actually? The last thing was what did you say?
So my point is that it's I get it that quantum computing and especially the sort of the specific type of approach to it, right? Like that where people compare a QPU to a GPU, as in like it's something that is just sits aside and it benefits from a CPU and integrated into a system like that. This kind of feels like it feels like it's restricting a little bit the more creative side of things in terms of maybe not creative, but like the more visionary version or part of quantum computing. As in, it seems to be really focused on solving specific problems, just because of the speed ups and the stuff like that. But it does not explore, or I haven't really come across any writing or any content out there where someone explores outside of this box, right? Like, okay, there's the whole thing with the quantum internet and stuff, but it's maybe not. This is not what I'm talking about. I'm trying to think about like I always expect maybe the paper to cover a bit more outside of these specific box kind of usage of quantum computing. Like, can we be, or would it be possible to kind of I don't know, do something else than just like those really specific purpose specific algorithms? But maybe it's, I don't know, maybe it's just too early, right?
Yeah, that's actually a good point. And now I get what you're trying to say. You're trying to say that you have to think out of the box because the thinking regarding the you can say the view towards the quantum computing has been restricted to algorithms. Uh, Basically, trying to say how the O'Reilly's books approach you can say quantum computing, right? Uh, sort of that. So I don't think that it's early for that. It's just that nobody has actually been actually trying to had a good implementation in that field. But I guess I might be wrong because this idea is seems to be new. Yet this is so you can say uh, relevant and a necessary part of the community. So I think someone has might have worked on this, and I think it's just that I don't have information about it, or we haven't come across it. Yeah, was it's a very relevant field, and it's you ask relevant questions actually.
Yeah, I mean it's like how, because I don't know, I don't want to maybe deviate too much away from the actual paper, but I don't, I feel it's kind of like, I don't know, it's general and it's informative, but it didn't, maybe it's because we're all like already deep into these in terms of learning and studying, and so it kind of feels like, yeah, it's kind of a nice overview. but I don't know. I have the impression that it will be interesting to see some work, done. It's like a bit the same when you take a look at these, languages like Silk, that they try to really go one level upper. I know that Amir is not super excited about that because of Q Sharp already does a lot of a lot of that stuff, but still kind of it caught my attention, right? That it's maybe an attempt to go in this direction. But what I find interesting is the paper doesn't really talk too much about like circuits and sort of the underlying kind of models that are used, but it's more like the business areas. And they do mention something interesting that he kind of says, like in quantum machine learning, for example, we don't even know whether a quantum machine learning machine would actually be general purpose type of quantum computer, right? Like the one that we have now in I don't know, like the ones that IBM offers, right? Maybe it's something really purpose specific for QML, right?
Yeah. So yeah, this point actually today when I was giving the webinar, one of the questions also raised this point. So it was a simple question that he was asking me for suggestions regarding the languages which you can learn to learn to come you can say perform computation on quantum computer. So then I realized that I said a sentence that it's quantum computing, although it has the term quantum in front of it, it's still computing in the end.
Mm-hmm.
So at one point or another, we'll need computer scientists to make actual algorithm on quantum computers. Uh, it's just you can say a matter of time when we get a viable and you can say a less error-prone quantum computer, we'll need to devise algorithm. So you can't expect the computer scientists to learn every tiny bit of physics in order to do that. So yeah, at some point of time, we will need an intuitive language, a high-level language which performs you can allows us to encode or code the algorithms. SILQ is a step in the right direction, I would say, when you consider the high-level language aspect. And yeah, so I agree with you on that. I get what you're trying to say here. So but
Yeah.
yeah, this is also this point that is it too early? This question, yeah, it's a very counterintuitive question because it doesn't have an actual answer because it's never too early. Actually, it's never too early.
Yeah, but look at this.
But
For example, like I remember when I was studying, like back studying computer science, right? Until you take like a course on software, like software modeling or software engineering, like all you're doing is you're learning, of course, the basics of programming, and then hardware stuff, and in the more of course, a little bit of physics, a bit of math, and all that stuff, and you kind of deep dive into algorithms and complexity and all these kind of things. But it's really at that one specific point in time where you start and doing some lectures on, or running, like going through some lectures about like how do you model a system, right? And how do you build a complex system? This is sort of the analogy that I'm missing, and I'm kind of whether there's a quantum analog of these, right? Like maybe there's no, like maybe there's just quantum computing is just one thing that you model in a bigger classical system, the same way that I don't know, in the perceivable world, the real world where we live in, like you don't perceive the quantum stuff because we're just too complex and too high level, and so we kind of behave in a way that's what we call classical. But now it's a bit weird because now you're building machines that are like in the classical realm in terms of size, but they do exhibit some quantum behavior, right? So maybe it's like I don't know, but maybe I'm just deviating a bit too much from the discussion.
no, these are good questions. Actually, these are very intuitive questions. Actually, so talking about the paper. I also like that he specifically said that what are the points that he won't be covering in the paper, in which he, you can say, basically covered the things which were, or you can say, more famous. You can say things which are much more popular in the community, like quantum cryptography and stuff like that. Yeah, I also like that aspect of the paper. So, any comments or anything you want to add?
No, I mean from the actually from maybe it's a question to you both, like from the topics that they're discussed in the paper, like which ones have you been kind of diving into the most recently? because I mean we're all learning on this, and I know like I expose a lot of the stuff or most of my stuff to the channel, and I sometimes get the feeling that I'm a bit too jumpy, and it's like every video is like, yeah, now I'm starting a new thing and something, and then I have 10 other things, 10 other topics open that I never end up closing up. And I'm curious about, like, because Amir like mentioned, he's got like a long list and stuff like that. But I'd be curious to know like which other topics you're really diving into right now from the ones in the paper.
Personally, I am more often, you can say, I like the quantum internet concept. It's not mentioned actually in the paper, but no, it is mentioned. Sorry. So I like the quantum internet aspect, and I'm working on it. You can say, yeah. Personally, I like that field of the quantum computing because you can say, before I learned about quantum computing, I was already into networking. So quantum internet was, you can say, a cherry on top for me. So yeah, personally, I am into quantum internet and stuff.
Okay. But like from maybe because I haven't really dived into quantum internet a lot. Like, can you kind of give me, I don't know, like a sort of an overview on like what are you interested in from the quantum internet perspective? Like, what's even that? Like, what from, because this is really like for those who are watching live. I mean, we are all learning, and none of us is an expert. And so, don't expect here to learn a lot, but just like, I hope that this at least exposes the types of questions that like kind of bother, at least bother.
Exactly. So I'm no expert myself. I've just started, you can say, going through the papers and all. So quantum internet basically is you can say a broader way of teleportation to keep you can say put things simply. You're just teleporting stuff, but on a larger scale. Although there are principles involved, like you try to write protocols, or the protocols which you be familiar with on classical terms, like the protocol for packets and TCP, etc., etc. So yeah, you try to implement those protocols on the quantum level, because when you're talking about you can say quantum level, the things are more prone to error. So, like in case of TCP, the three-way handshaking theorem, the same things need to be applied in the case of quantum internet. So yeah, those it's more or less same right now because it's a new field, and yeah, I think that should be fine. That is all I want to add right now. So, if Amir wants to add anything, then he can go on.
I like how we each find our own areas, because often it's they're not overlapping. Like, I actually don't care much about the quantum internet. So and to your question, Daniel, I've started to narrow that list down, because that list was getting too big and I was trying to understand it all. And at this point, I've chosen to just focus on quantum machine learning for a period of time until I think I've gotten at least a good foothold in understanding where the state of the art is with that. So.
And within quantum machine learning, like, you're exploring some specific areas, or because I recently really started to dig more into at least the variational stuff, right? But like, other than the variational thing and kind of the algorithms that are more geared towards improving specific mathematical constructions on classical machine learning or like deep learning, like, is there anything else that you're exploring in there?
Well, I'd say you're ahead of me in this regard. So for me, it's even just getting some of, although I have like gone through a few tutorials, it's really understanding the feature spaces that we're trying to encode data in quantum machine learning, more so than I think like a common problem is, or what I've heard is that people try to basically take their classical models and those approaches and just apply them to quantum. But we've got different problems here with data loading. So where we can't load a lot of data, we can actually transform that into a much richer, higher dimensional feature space. And so while I can parrot that back right now, I don't actually understand that at a deep level, and that's what I think I'm going to focus on. But this also ties in more with my day-to-day work. What I'm trying to do is actually just for a period of time block out some of the rest of what's going on, trying to get it all, trying to like, you know, and just see what will happen if I can put some focused energy in one area.
I mean, that kind of makes. I mean, it seems like at least you're a bit more like going in depth than, you know, what, like you pick a topic and you kind of go a bit more in depth. Whereas I'm more like I go wide and then I tend to, you know, go a little bit deep in some spots, but that might not work the long term. Actually, in the paper, like there was some stuff around like QRAM. And because you talked about like data loading and higher dimensional spaces and stuff, like, are you familiar with the QRAM concept? Have you dived into these recently, or is it like also an unknown topic to you? Because I think I had the wrong misconception of what that actually meant. I mean, I did a really early video on the channel about like a quantum neural network, and I remember that one of the comments that I got was like, yeah, that's all cool, right? But the problem is that we you know, loading the data is just, you know, it's just killing the purpose of using that.
So, man, I feel like you lobbed that to me because I just got involved with a project related to QRAM like maybe 2 weeks ago, and this is Sarah Kaiser's project.
Oh, I saw, yeah, it's the one that also got a unitary fund, right? Like,
yeah. And I'll say involved in a loose way. I've just sat in on the screencast she does, and I've read through the paper that Olivia wrote. And I started to contribute to the project by looking at one of the bugs. And it was funny, I got sidetracked because I wanted better visualization tools. So I wrote a C# to Chasm exporter that I could then take all of, you know, the benefits of Q# you write in this higher level language that, you know, has some constructs that, you know, make it easier without having to think explicitly in just the rolled out circuit. But I wrote something that basically evaluates C#. It's written as a simulator, but it spits out Chasm. And then what I did with that is I had like a Chasm file that I then took into Qiskit, so I could use some of the visualization tools there. So yeah, so I haven't actually done any work on QRAM, but I'm ramping up in that a little bit. What is neat about it though is exploring how we're going to address quantum addresses in memory, and like how we're going to not only get back a single qubit, but maybe get back. And this is what's weird, is thinking about addressing memory in superposition, which is just not a like concept we understand in classical computing.
But so you mean, that's actually interesting. So you mean you address memory in a superposition, as in like you're referencing memory positions in superposition, but like the stuff that the memory positions are holding is still classical data, or like we're talking about like ways to physically store. Because that would seem to me impossible. Like if we think about storing all the data that it takes to reconstruct a quantum state. I mean, isn't that the point of, you know, not being able to simulate a quantum system, that it just, you know, takes exponentially more data? I mean.
Yeah. So the paper that Olivia wrote for the project, that's specifically to address QRAM registers or of memory. So not necessarily, you could store classical data, but it is very much for the quantum, quantum state you would be storing.
So you mean you actually store, like, let's say if I have an equal superposition of like a 2-qubit system, you assume the QRAM is able to store the information of that state, or?
I believe so. I would say it would still be explicit though. So you are going to have operations where you're saying write this source qubit to this target address. So it's not like you can kind of snapshot the whole system, but you would still have a lot of operations. And that's the part of this project, is to experimenting with those in a simulator, and to also analyze how much extra code does this add just to address this memory and write back to it.
That's interesting. I mean, and then you would kind of address the memory, addressing the memory in superposition. That is definitely something that takes a bit more of an effort to kind of grasp, I guess. It's it's kind of a bit like in Zilk, like you kind of can have variables that are in superposition, right? Like integers that are in superposition, and that's also kind of like an interesting concept there as well, I guess. But I still don't. Maybe I really have to dig into this as well, because I still don't get like how can this make sense at all? Like if I mean, you're not going to be able to store the state of, like, say, a 50 or a 70 qubit system, right? So you can store. I mean, if you're saying you're storing or you're kind of binding qubits to specific QRAM addresses. Okay, that is one thing. That, yeah. But still, like, you have a system that's got entanglement, and that, like, you're kind of putting the qubits apart. I don't know. It's a bit foreign to me right now, so it's definitely something to explore.
I mean, your intuition is correct on that, of course, because one qubit memory requires quite a lot of auxiliary qubits just for the address register and for the target register. So, like, there's quite a lot of overhead right now, but that's the fun part about it is working out some of those issues now, actually trying to implement some of these papers. And what's cool is Olivia, who has written a paper, is also involved in the project. So it's a neat community effort, I think, right now.
Yeah, that's definitely cool. Is it? I mean, I really haven't seen any other project about that. Like, at least not something that you can really. Because I saw this because you tweeted recently about it. So I'll definitely take a look into this. I'm more approaching the sort of the QML side of things purely from the variational aspect of, really what does it mean? Like, sort of like trying to understand a bit more, the details of an actual variational algorithm. And, like, one thing that really kind of bothers me a little bit is it's not that it bothers, but it's like definitely something that's kind of, there's a lot of stuff to explore there, and it's really in the design of the ansatzes, so to say, right? Like, how you see the typical thing where you've got, like, rotation layers, you've got, like, gates that entangle qubits, and that's supposed to kind of give you a good enough ansatz, but it feels more like trial and error type of thing, rather than, yeah. I don't know. It's definitely, first, when I started exploring and learning and all that stuff, I thought that was not an interesting place to dig into, but the more I dig into, the more I get sucked into it.
I'll connect that back to the paper too. If we consider the environment that 2018 is, I would say, very different than even today for quantum computing. Maybe, well, yeah, I'd even say that probably for even those who've been in the field for such a long time. But, like, if you think about Preskill, I think he's still writing for the academic audience, and what I find is that being more of an engineer and experimentalist, I think that, just say engineer, I shouldn't say experimentalist, because that would be reserved for people who are probably building actual hardware. But being an engineer, it's like, I almost feel like the work we do to figure out, like, reducing T-gates and actually implementing algorithms would just be a single line on any paper, which is an exercise left for the reader, meaning that, like, everything we'll do in practice, just an exercise. So just to compare this to another conference that I attended, was the ISCA conference, and it's put on by the IEEE. And it was cool to see quantum computing papers and discussions about reducing like T counts in adders, quantum adders. Like there is a, I think it just depends on what communities we're floating in, because like there are really interesting papers at that level which are so hyper focused on just reducing the number of T gates, and that kind of work is going on. That's the kind of work that will help us realize, I think, some of these quantum algorithms sooner. Like if Preskill, I don't see Preskill writing a paper on that. It's just so narrowly focused. I'd be curious to hear what you guys think as well.
I mean, to be honest, I'm not like really familiar with the work of anyone in the field. It's a bit like I feel like I'm kind of quite like disconnected from like which person is doing like what type of research and whatnot. Like and I should probably do a bit more research in this myself, because I feel like I'm also making a dishonor or a disservice to the people actually writing and moving the field forward. But it's like, I don't know if I understand what you're saying. What you're saying is that like that you're not gonna kind of see some of these really narrow type of work kind of really get out of the box that I was talking about, right? Like it's rather it feels like if you're doing some of those really low level, like I mean low level not in terms of hardware but in terms of like reducing the T counts and all this kind of stuff. That those are like those kind of micro steps that are really taking us close to being able to have something that it's a more usable set of tools to then really do and explore the kind of more creative things you can do with quantum computing.
Yeah, I also feel that different people can have different perspectives. So as Amir said, that from an engineer's perspective, you can say things are more hardware oriented. But yeah, as an academic perspective, I think John Preskill is doing great work. Yeah, the academic perspective has also needs to be considered. So it's a community thing. Different people can have different approaches. There are, you can say, millions of problems to solve quantum computing itself. So everyone taking one problem or taking one aspect of the situation can actually help. You can say all around. You can say the society to or this community to grow as whole. So yeah, I think this works in advantage of for quantum computing. That's what I feel.
I'm trying to take a look at I'm actually going through the paper, scanning the paper quickly in terms of what else was there. I mean, there's even a mention about quantum games, right? Like, I don't know what's your stand on this, because I did go through some of the stuff that like the Kodoku that has like the Minecraft type of map generation kind of thing, where it's using an IBM quantum computer to kind of like do part of the generation of the terrain. But I haven't like, I mean, you've got all the educational types of games. There are a bunch of them out there. But I don't know, it's an area where I also feel a bit skeptic that this is kind of like a tool that really helps you learn. A lot of people talk about like, quantum native generation growing up with like sort of a built-in intuition in terms of what it means to operate like in a quantum setup on a quantum world. But I don't really know whether this is something that is really gonna end up this way. I don't know. What do you think? Like, because I think it's a really short. It's like 10, 11 lines where he says that quantum games could open a niche. Okay, that's another topic. But like, let me see. Perhaps kids who grow up playing quantum games will acquire a visceral understanding of quantum phenomena that our generation lacks. But I'm not so sure whether this is really something that you can kind of, or that can really happen. As in like, we grow with classical intuition because we learn, and I'm saying this because I have a little kid, right? Like she's just 15 months, and I see how I really see how she's learning stuff, and it's literally, interacting with the environment, and it's this kind of, repetition type of repetition driven type of learning that, it's almost like saying, you would kind of have to put a kid into an environment where things behave quantumly to really, to really get that level of visceral intuition or visceral, feeling in terms of a generation. Like, I don't know if quantum games are really going to make any difference there. And maybe just because I'm not like seeing. I don't know if Amir, you mentioned there's some feedback in the channel, in the chat, but I really can't see anything. I'm gonna try to see if I can.
I was meaning in the voice channel. It's been gone since we started muting it. It's just when we all have our microphone. Like, yeah. I'm getting a little feedback now through.
So you're talking about audio feedback, not like people's feedback.
Yeah, sorry, I meant audio feedback, not like text feedback.
I have chat open in case, like, because there's always people watching, and then I'm trying to see. There's a couple of comments, like, but there's nothing, no one complaining about it. And it's really, for me, the first time that I'm streaming just voice this way, and then I have the OBS set up, and my mic is not working perfectly, so I kind of am just using the built-in mic, which is not optimal, and maybe that's why you're getting the feedback. So, but yeah, I'm definitely buying a better mic and speakers and a better setup. I'm going to improve on this. But anyway, what's your take on the quantum games thing?
Oh, it's a funny one because this is my field, so it's interesting to even see this small section in here, and it gives me appreciation because I know how highly intelligent John Preskill is. Like, just the way I experience, like, from all his papers. So yet it's still funny to have someone comment on another field. Like, I don't know if he plays games, but it's kind of the same sense that anyone, like, when people thought it was cool to gamify everything, they were like, hey, can we gamify work? Can we gamify, like, voting? It's at that level of, like, hey, we can just slap a game on it and it'll, so like, while Decadoku also does a lot of work in quantum games, his background isn't video games. So I love what he's doing to, like, bridge that gap between quantum computing and video games. I'll just say, as an actual gamer and someone who, like, has been working in the game industry for over, close to 17 years, like this is the kind of, like, it just feels far removed from where actual game development is at. Like, where, like, to me, most of the quantum game work is just number generators right now. Decadoku started to move into some more interesting areas with his last one. I think he wrote a paper on quantum graphs and using that as a, like, rudimentary way to handle some decision making in the game. Yeah, overall, I'm skeptical. Working in games, I think the only benefit quantum that we'll see in games is potentially on the game development side. So if we start have algorithms for ray tracing or generating lighting or complex environments, or mesh simplification, when you have these high resolution meshes you want to decimate. So that's what gets me excited, more so than, like, seeing a quantum computer used in an actual video game.
Yeah, so you mean the actual, like, the helping in speeding up, or have even, like, completely different approaches to actual sort of underlying processes and algorithms that are needed for for building the game, or because it's kind of, I see that split too, right? Like, this is one side of the coin, and the other side being the actual game mechanics. Like, if you think about something like, I don't know, quantum chess, right? Like, where you can make moves in superposition and stuff like that. This is then a different thing, right? Like, it's and this is where I kind of have, like, I'm more skeptic in terms of quantum games being able to actually teach people, how, or kind of teach people or help people to build up intuition, quantum intuition, so to say. Maybe the quantum chess is at least it gives you the aspect of superposition, and so that when you have to, because it has the competitive component to it, like you're playing against someone, and then it's more like, I make a quantum move, so to say, and then my opponent has to think about, okay, what has just happened, and then what's the state of the game, so how can I make the next best move to beat that. That might still, I think quantum chess might be an exception to this, but I don't know, things like the Hello Quantum game from IBM. I don't know if you've played with it. It's more like the puzzle type of game. This is the game, the same like the ones that I'm doing from time to time. Like it's more like puzzles around quantum stuff. But I'm not so sure if that's something that helps a lot, other than just practicing. I don't know. Have you played Hello Quantum? Like the one that like there's an actual app in the App Store.
Yes, I have played that. And to add to what you were saying, that yeah, it makes sense because what I believe is quantum mechanics is not actually hard, or you can say quantum physics is not hard because of the numerical aspect, or you can say theorems and all. I think it is hard because the ideas which we have to accept while dealing with quantum physics or quantum computing are quite counterintuitive. We are not used to seeing those ideas around us. We live in a classical world, you can say, and these principles become much more relevant when we come into quantum realm or subatomic realm. So when talking about, you can say, quantum games, the approach should be to build intuition around these ideas, and not being centered on, you can say, the principles or how things work. We're trying to build we're trying to embed the ideas that we feel more comfortable, or that whenever we come across these ideas we don't feel like, okay, this is something new, or this doesn't make sense to me. I think that should be the approach, and that should be the way the quantum game should move further, I guess. Yeah, that's my take on this quantum game.
Yeah, I think we're pretty much aligned in there, and the maybe to switch a little bit topic. There's a slight mention in the paper about digital versus analog quantum simulation. Like, is the analog quantum simulation that Preskill talks about? Is it the type of Xanadu, like the continuous variable quantum computing thing, or is it something else? Like, I don't know if you've gone through that part, or if you've ever come across the continuous variable quantum computing.
I'm reviewing again that section right now.
It's 6.10. It's a short one as well, but like it says that analog quantum simulators are hampered by imperfect control. So they say it basically says the main problem there is that they are much more error prone. That's kind of what confuses me a little bit, because I kind of thought the opposite. That's why the photonic quantum computers seem to be. Maybe I'm getting it wrong. Maybe it's just the advantages being that you can run those in room temperature, right? So you don't need the whole thing with a dilution refrigerator. But I just want to, because I want to know whether this is this what they're talking about or not. Like if not, like something to dig into as well.
You clarify continuous variable quantum computing.
So the idea is, like, in the gate model, right, that we're all familiar with, you can think of these as being digital quantum computing, right, in the sense that you've got like the zeros and the ones, so it's from that perspective it's digital, and the analog or the continuous variable quantum computing is a bit different. So instead of measuring a digital system, like let's say the spin, right, like the spin property, it's sort of digital in the sense that you get like the spin like +1 or -1. What a CV quantum computer does is it's measuring, for example, position and momentum, and so this is like you're actually you're actually getting an actual real value in your measurement. It's not you're getting a 0 or a 1. You can get like, I don't know, I probably get it wrong, but like 2.53, right? Like, or whatever. Like you get an actual real number, an actual, like, you know, it's not discrete in the sense, because I think it's maybe more than digital. It's discrete quantum computing versus continuous variable quantum computing. And so the idea is you have momentum and position being the two operators that are that you can't know about simultaneously. And so then you've got a different set of gates. Like you don't have the traditional Hadamard, NOT gate, control NOT gate, and stuff like that. You have different gates. Like you have the squeezing gate. That basically what the squeezing gate does is for, and I might get this wrong, but it squeezes your position, so it kind of spreads your momentum, right? Because that's the when you squeeze one, you're spreading wide like the other one. Like those two variables or those two observables kind of behave this way. And so by doing and playing with operators that modify the position and the momentum, you kind of get the same type of computational model, but it's continuous instead of being discrete, right? And then you can have, there's like a nonlinear gate as well. It's the Kerr gate, and then you've got like the beam splitting gate is the one that creates entanglement. And it entangles the position and the momentum of what they call quantum modes. Instead of, it's not qubits, it's quantum modes what you're working with. And I was watching recently one of those the biggest ideas of the universe from Sean Carroll. Like, and when he talks about quantum field theory, he really introduces the concept of a mode, as in being a mode is a component that it's one of the parts that a quantum field is composed of. So it's composed of multiple modes. The modes can be in superposition, and the modes is like a continuous variable thing. So that's the difference. And it's I really came across these, unfortunately, like really early in the channel when I was doing like I wanted to review a project from Michał Stenhue. Like it was called the Yellow Submarine project, where he was doing some stuff with CV quantum computing, and he was like, man, you shouldn't get into these. It's like, it's too complicated. Like, you just go through the discrete or the digital quantum computing first, and then once you feel confident, go in this direction. But I don't know if this is exactly what this refers to. Probably. Otherwise, I don't know what it means analog in this case. Have you ever come across this idea, or is it the first time you hear about it?
It's the first time I'm hearing anyways. I think I've heard the term continuous variable, but it's the first time I'm hearing that explained. That's an interesting take because it's a little bit different. Oh, sorry, go ahead.
No, I was gonna say, you go and like if you go to Xanadu, like they've got like a lot of resources in that, and you also have an interactive visual tool to play with these, and so you kind of get a visualization of the wave that represents the position of your mode, and the wave that represents the momentum of your mode. And then you can, it's also like, the model is also a circuit model, so you really drag and drop the gates and you see the modes, the waves change. But then it gets really funky when you take a look at the stuff you can do when you measure, like, because you can measure, as I said, position, you can measure momentum, but you can also count the photons, for example. Like, I don't know, there's a photon counting measurement, which kind of makes it a bit weirder in terms of, if you compare this with the quantum computing we're used to. And then if you take a look at the math behind these gates, like, to me, that was already like, if you take a look at the sort of math proofs of certain things, like, because it's just linear algebra, what you do typically, it's really understandable. But here you're getting a lot of different stuff in there that I'm really far away from being familiar with. So I kind of dropped that, but it's definitely something interesting to take a look at. I mean, I recommend it. It was just, I don't know, when I saw the Kerr gate and the beam splitting gate and all this kind of stuff, I was like, what the heck is this? But it kind of somehow makes sense. It relates a little bit because you have the concept of entanglement, you have the concept of, of measurement, and you have all these different things, and you have like the an actual Fourier gate as well, like, and even there's like I think there's even some resources where they implement like the analog version of the quantum variable, continuous variable version of teleportation, of Grover's algorithm, and those look fairly different. And I think it's a nice exercise to kind of see one algorithm you're familiar with, but from a completely different model. It was a good exercise, at least for me.
Yeah, I hadn't considered it the way you were describing. I was looking at, and I was reading initially Analog Quantum Simulator more as being able to like have analog knobs instead of these digital gates we use. Think of varying, like instead of an X gate, you have like just a general knob where you can control X rotation.
Okay, so just having parameterized, like really fine-grained, parameterizable kind of gates. That's what you mean, or?
And you can control that and twist all the knobs in potentially in parallel or maybe in tandem. But you know, you can control the rate at which you turn the knob and basically you can vary that and it almost makes me think a little bit of annealing, although you know annealing is based on that adiabatic theorem. So yeah, there's like this sense of like not I don't really have much more to add. I think that's just how I was understanding. But what you're describing is cooler because it's almost like turning the control, like there's more physicality in the actual controls you have, and those are just represented in a way that you can, like, you know, construct gates with and create algorithms. But
and the cool thing is that it's, you know, this is something you get when you build a photonic quantum computer. And there's a guy, I forgot how, I was trying to look for this now, but I kind of forgot, I have it somewhere written. There's a guy somewhere who's posting, like I met him through one of the Facebook groups about quantum computing, and the guys posted like the full specs on how to build your own photonic quantum computer at home. Like, and I think he's like, I don't know, it was like about like $15,000 or $20,000 in terms of, you know, the parts and all this stuff. And he puts in there, you know, all the blueprints and everything, how you can connect everything. It's really implementing like an actual CV QPU, so to say. I really haven't digged into this, but it's the cool thing is that in theory you could do this at home, right? Like if you just buy the parts and the lasers and all that stuff, and you really know how to manage the equipment. I mean, that could be like, if you have the money and the time to do this, like that could be super interesting to learn as well. I mean, you'll probably get just like a couple of modes or something, so you wouldn't get something. I think he actually posted the specs for like a 5-mode quantum computer or something like that. First I thought it was just BS, but then I was reading these and I was like, no, that actually, he's actually doing this. So yeah, but I don't know. I mean, who picked the paper, by the way? Was it like Giri who picked the paper?
I did. I picked the paper.
You picked the paper. Okay, cool.
Yeah.
I feel like that was, I mean, it was a good read, but I kind of feel like I'd like to have more, a more focused kind of reading theme as well. But I mean, as we are all also exploring different areas, it might be kind of difficult, but it might be at the same time, I think, enriching to you know, we could maybe just kind of rotate and, you know, let each of us kind of pick a paper. And so I don't know, for example, we do something on QML, or we do something on the quantum internet, like stuff like this. And at least kind of one of us or one person in the discussion probably has more knowledge than the others, but then it can, I think it can kind of help with learning as well.
Yeah, that's a good concept. Yeah, nice, good concept.
Sounds good. Any closing thoughts?
I mean, I think from my side, these are really closing thoughts. Like I don't really I feel like I don't have anything to add to the paper. Like I could be talking for hours, to be honest, but I could be talking for hours about like different things that I'd like to explore in there. But at the same time, it feels like that's not, the most productive thing to do like anyway. And I prefer to have something a bit more kind of concrete to discuss next time. I think my closing thoughts would be here. The paper gives a really good overview on everything and also the verticals that the field is touching, and it does a great job in not hyping things up. Like it really, it's a repeating theme where Prescott, he's like, we don't know, right? Like this, yeah, maybe, but we don't know. And these I very much like because it's it really paints a more realistic picture than a lot of the stuff that you see out there nowadays. That it's a bit more, it feels a bit more marketing material type of thing. And but that's really it. Maybe I would have liked, I don't know, I would have liked to see some of the sections be more developed, but it's it kind of pretty much aligned with and I think it's aligned with your view of things, Amir, as well, in terms of like the whole cryptography space and all this kind of stuff is left to be decided. It's also something that I'm not super interested in right now, so I kind of like that. But I don't know. I had fun reading the paper, but I definitely want to have something be more concrete next time. You guys, any closing thoughts?
Yeah, I agree with you. The paper actually, what I like about paper that it creates hype about quantum computing while still remaining, you can say, close to the ground. It states realities of the problems which we are facing with quantum computing right now. So yeah, I like that aspect as well. So that would be my closing thought.
I enjoy the paper just as an overview, paper. I think it was probably timely around 2018 as things are heating up even more. I'm looking at his summary points, and I think most of them we are doing. It's interesting that you outlined the analog versus digital simulator, because that's one area he calls out again in the summary. I don't know if we are making as much use of that. I don't have a sense of that just in terms of the papers. Not that I follow everything. That's probably one area that hasn't come to pass where we're making the most use of the analog capabilities of our current quantum computers. So I think that's, yeah. The other ones, I think we, like, whatever, he's not like off this, like saying that we were going to do all these things, but I do think we've kind of, other parts of this summary we actually have been focusing on, like the hybrid quantum classical algorithms have certainly been worked on these past 2 years, and then he was thinking that, as more people come in and experiment, when we have actual quantum computers, that we are starting to develop new heuristics, and we can just see all that from all the variational variants we have now. You can just add B to something, it's probably a paper already out there.
Yeah, good point. I mean, what you mentioned about like the analog stuff, like as in being not something that, or something you feel where we're not using the full potential, like I mean, just as a funny remark, like I was reading recently, rereading some of the papers or some implementations on some of this stuff, and it was funny to see that the author was like, I don't remember what was that, but they were counting the photons, and they're like, yeah, if it's like below 5, we'll consider a 0. If it's over 5, we'll consider a 1. So they're like, it really felt like not really fully utilizing the power there. But yeah, honestly, I mean, I don't know. I again, as I said, I think I like the paper as well. I mean, I like the document person, and I was not personally involved in quantum computing in 2018, so I kind of like don't have the context and appreciation on like the impact this could have had. But now I see. I mean, you see the impact of, you see the hype in this, like now with COVID and all these kind of things, and it, I think it's good to have this type of view as well. Cool. Yeah, I don't know. I mean, I enjoyed the discussion. Maybe, I mean, if you guys, we can like discuss and talk later in the Discord. I'm probably gonna put a, I don't know if you can make a, wait a second. What have I just done here? Am I still here, Will? Yeah. I wanted to kind of create an invite or something for people that have been watching these, but I'll probably share one in Twitter anyway after these. So if someone wants to join the Discord channel, at least they can do this in the next day or so. Yeah, I mean, I don't know. It was fun. Do you guys want to do sort of one a week, or do we do twice a month, or like what do you think a good cadence for these is? And is it like a discussion like this one? Like it's good to like time it around like an hour, or I mean, I guess it depends on the paper, right? But I don't want to, like, I don't know. What do you think?
I'm open. We could probably figure this out in the channel. For other like paper clubs, or I've seen 30 minutes work sometimes. It depends on, I think, how many people are involved and how much we have in terms of opinions.
Yeah, I guess that's probably what makes sense. I mean, there's no reason to kind of limit that anyhow, but rather leave it to the paper, and if it's a topic where we disagree a lot, I think it's going to be fun. If not, then it's going to be a 15-minute chat and that's it. No, but I like it. I mean, it feels like I'm talking every week, 2, 3, 4 times a week, like just to the screen when I do the videos, and this is a bit refreshing to actually know that you're talking to someone that actually answers. So from my perspective, it's been fun. Yeah. Cool. Then I guess we'll leave it here. Thanks. I mean, I want to thank everyone who's been watching. There's been like, I'm looking at the stats, and there's been like a continuous amount of good amount of viewers all the time, which I'm happy, because it seems the topic was at least interesting to someone, which I think it's kind of beneficial as well. And it's not really the typical expert type of discussion where someone kind of gives the expert kind of talk and then everyone listens, and it's a bit more. I mean, I'd love if we get more people from the Discord to join, to just have like 4 or 5 people discuss this. To have 4 or 5 people discussing would be cool as well. Yeah. Then I don't know. I guess we're done. So thanks.
Yeah, I mean, I like having different opportunities to connect, and you even have different styles on your own channel. So like you've got the turn the qubits off. You've got I think these are all different like great ways to engage, and this is kind of low key, just way to like hang out, discuss quantum things, have some structure around it because we've had a paper to read. So yeah, I like that we have it, and hopefully we can just get a few more people on as well.
Yeah, cool. Then yeah, I mean, see you guys around, I guess. I'll be ending the stream in a second.